Because if I have an AC signal and I just got it going across a resistor, and I identify that this resistor is 1 kiloohms, no matter what I do to this frequency of my function generator, whether if I increase it or decrease it, my resistance of my resistor is always going to stay at 1 kiloohm. Well, if I replace that out with a capacitor, and I put a frequency across the capacitor, I have resistance. It's our X sub of C, and we'll talk about it later on. But what's going to happen with a capacitor is as I increase or decrease my frequency, my resistance of my capacitor is going to change. And then the resistance of my capacitor is going to be based on whatever my frequency is of my function generator is. So that's why we call them reactive. They react to the frequency that's being changed on our signal. So our resistance is going to constantly change. So to take a look at why that is and stuff, again, we're not going to go too much into the mechanics of how a capacitor works, but we'll just talk a little bit about it. Is that I have two conductive plates that are sandwiching an insulator. So electrically, in between these two conductors, there is no real electrical path. It's actually got, these capacitors, they get that for a dielectric, which is our insulators. Could be air, mica, all different types of paper, any type of insulator and stuff. And so there is no real electrical path in there. But the characteristics of a capacitor then, what it does allow us to do is it allows us to hold a charge. We can charge up these capacitors, and then it just is basically if I have, if I draw up a circuit that looks, cross resistor. Okay, so here's my DC source, and it might be at 5 volts. Okay, so that means I would get 5 volts going across there, and I would continuously get 5 volts going across my resistor, as long as I have that power supply in there. Well, it's kind of the same thing with a capacitor. If all of a sudden I put in a charged capacitor, it acts just like a source once that thing is charged up. I can just throw in a capacitor, a charged capacitor, and what's going to happen is that the charge that's being stored on the capacitor is going to act like a source, and it's going to go right back into our circuit. And then eventually what happens is that since we don't have anything to maintain that charge, that capacitor is going to go it's going to go dead on it, it's going to lose its charge, and then my current flow is going to stop. But it's just, at one point it's taking in all the energy, and then at another instance we can have it putting back into our circuit and using up the energy that capacitor is being stored on. So basically how these capacitors are kind of working is that when we hook up a voltage source up to it, we're going to separate all the electrons and the protons onto each individual plate. All my protons are going to be going on the positive side of the battery. All my electrons are going to be on the negative side of the battery. And then once I go ahead and I remove that source, all those electrons and protons are staying on there. They're going to stay electrically charged on that capacitor. And they're doing that by, just like magnets. Unlike poles attract each other. So all these electrons with this very thin insulator in here are trying to attract each other. But there's no place for them to go. There's no conduit for them to go from one side of the plate to the other side of the plate. And so they're being held together by their attraction to each other. Because remember, the electrons are trying to seek the protons, and the protons are trying to seek the electrons. And they're just going to hold themselves in place onto those plates. And then that's going to hold us a charge. But then if all of a sudden I give it an electrical path, put in a resistor, now what happens is now I give it a current path, and all these electrons then are going to start to flow, and they're going to go through the resistor, and then they're going to start seeking out all the protons. And once they neutralize out, and I have just as many electrons and protons on both sides of these plates, my capacitor just kind of loses its charge. There's no more separation of the electrons and the protons, and then that capacitor is going to lose its charge there. Okay? So that's kind of the basic makeup, and I'm going to let you do all the other reading. We're not so much worried about the dielectric strengths of them and stuff like that. Other than that, we have a rating that we always have to watch out for, and that's our working volts DC. Not so much worried about on page 390, they have it where they talk about how much charge a capacitor can hold and stuff. We're not too concerned about how many coulombs can be stored on each one of the plates or anything like that. We're going to be using it as what is the applications for our capacitors are. So the ones on page 390, talking about the capacitance and stuff, how much charge it can hold, how many coulombs of electrons can it hold on each plate and stuff, not too concerned with that. But other than we should understand the concept of how a capacitor works. We are worried about the units though for it, is that just like our resistors, we had a unit of ohms, it was like 1 kilo ohm. Capacitors are going to have another unit, they're going to have what we call farads. That's the size of that capacitor. So the more farads I have, the more charge it can hold. And so for example, if we have a capacitor and then in our lab 17 there, it wanted a 1,000 picofarad capacitor. That was the value of it. We have no clue what that resistance of that capacitor is until we apply an AC signal to it. So when we're identifying what we need for components in our circuit, we're just looking at it, what size capacitor do I need? And that's going to depend on our application. Now when we're working with capacitors and stuff, and we start talking about how many farads it is, when we're talking about capacitors, the units are going to be either pico or micro. When you're doing your calculations, you might have calculations that have nanofarads or millifarads or something like that. But when it comes time to go ahead and ordering up these capacitors, typically you're going to be ordering them up either as picofarads or microfarads. And now with the new larger capacitors and stuff, now you can actually jump up right up into the farads, which are really large capacitors. So sometimes when you're ordering these capacitors up, we can see it. We know that our bill of materials is asking for 1,000 picofarads. Then you go to the website. You go to DigiKey or Mauser or some other vendor, and you look it up, and they don't have 1,000 picofarad capacitor in there. They might not have it listed. So what you need to do is, this is where all our conversions come in. We're always kind of converting our capacitors into ones that our vendors might be how they're displaying. Some vendors might have it as 1,000 picofarads. Others might have it as a microfarad. So if I have a 1,000 picofarad capacitor, how many microfarads would that be?
001.
Yeah. So I'm going to go from picofarads, and I'm going to just move it over 1, 2, 3. I know it can't be in nano, so my next one up is nano. So I'm going to go with another 3. 1, 2, 3. Then wherever my spaces are, fill them in with zeros. So 1,000 picofarads is the same quantity as a 0.001 microfarad. Okay. So if you don't, so if you're looking in your bill of materials and it asks for 1,000 picofarads, and you can go and you look into your part kit, and you don't have 1,000 picofarads, you might have one that's have 0.001 microfarads. And those are our units. So they either go in picos, micros, or actually in farads. Farad one, let's see. Used to have what happened? Just have a real large one here. Let me see if it's on my table here. I don't know what happened. I had a real large one. I had one.
Oh, that
What am I?
boom box?
The blue one, yeah, the big blue one.
The one for the
Huh.
car stereo.
Maybe Dan grabbed it. Yeah, for the car stereos.
For sale at Walmart.
All right, so then, so when we're looking at our different units here, we know that we have our units as in picos and micros and stuff like that. And on page, kind of jumping around here. On page 400, they talk about the capacitor labeling. I'll tell you the easiest thing right now to do is to keep your capacitors in the bag. There's so many different ways of looking at, depending on if it's a mylar capacitor or a ceramic capacitor. They use some real. It's not quite as straightforward as a resistor is. So let me bring that up here. Let's see. Let me see if those are on the printer, because I forgot to print that off for you. I'll be right back.